So we'll do some programming today. We have done 5 groups of instructions. The last one we did was stack group of instructions. We are left in the machine control group of instructions. We'll do that after we study interrupts extra. So the first program that we'll be doing today, now we actually studied the branching group as well as the stack group. So those instructions will be required here in whatever programs we'll be doing today. So the first program that will be doing is write a program to find the maximum of two numbers. So this is how we'll be doing this. We have been given two numbers, and let those two numbers be anywhere in any memory. Let's assume those two numbers are at 3000 and 3001. So we have two numbers, one is at 3000, another one is at 3001. We want to see which of these two numbers is greater. Fine. So let's load the accumulator first of all. LDA 3000. So write the hex code of LDA here, so you can see it from the chart. Then the LSB of the address, then the MSB of the address will occupy. So this will be occupying a total of 3 bytes of space in the memory. So what does this do? So whatever is located at the memory location 3000, that will be loaded in the accumulator. So we have loaded the contents of memory location 3000 to the accumulator. We will now transfer this to any other location. Move B comma A. You can write move C comma A, D comma anything. We are simply storing whatever was in accumulator in some another register. So you have to write the opcode of move B comma A instruction, and from the chart. So what does this instruction do? Whatever was in accumulator will now be transferred to B. So in short, whatever was in the memory location 3000 has been transferred to B. Now accumulator is actually it's not exactly free, but we can use it. We can now store another data that's located in the memory location 3001 and load it in the accumulator. So again, write the opcode for LDA, then you have to write the LSB of the address and the MSB of the address, so 01 and 30. So whatever was located at memory location 3001 will be transferred into the accumulator. So we have transferred both the data bytes. One was in 3000 and another one was at 3001. Both have been transferred. One is stored in B, another one is stored in A. Now at this point, what we can do is we can simply compare B. So we know this instruction CMPB, so it basically compares your B register with the contents of accumulator, and the status of the flag basically tells us what is the resultant, whether A is greater than B or B is greater than A or A is equal to B. So you have to write the opcode of CMPB here, and what this does, it compares A and B. The two registers A and B will be compared. The contents of these two registers will be compared with each other. The result is actually given by the status of the flags that we have already seen. Now Now we know from this instruction compare B. If A will be greater than B, the carry flag will be 0, Z will also be equal to 0. If A will be equal to B, carry flag will be equal to 0, Z will be equal to 1. If A will be less than the B register, the contents of A will be less than the contents of B, then the carry flag will be 1 and Z will be equal to 0. So we can actually check the status of the carry flag. So what we'll be doing after this is we will write an instruction JNC jump if carry is not if jump if carry is not set, or you can say jump if carry is reset. That means if carry is equal to 0, then jump to any memory location and to some address, and what that address will be, we will see that. I'm going to leave this address right now blank. I am not exactly sure what this address is. We'll see as we progress on. Fine. So JNC address. So you have at this location you will have to write the opcode of JNC instruction. Here you will write the least significant bit of the address. Here you will write the most significant bit of the address. So what does this instruction do? It jumps to address, whatever is the address specified here, if carry is not set, or in other words you can say if carry is reset. That means carry is equal to 0. So if carry is equal to 0, it will jump. If carry is equal to 1, it will not jump, it will move on to the next instruction. And what will that instruction be? Move A comma B. So whatever was in B, that will be now transferred to A. Fine. So we are actually transferring the contents of B now to A. B is actually carrying the data that was transferred from 3000, and that will be transferred here. So you have to write the opcode of this instruction. So what is our exact question here? We have to write a program to find the maximum of two numbers, and those two numbers were provided at these two memory locations, and store the maximum number at memory location. Say for example I will write it 3050. Fine. So whatever is the maximum of these two numbers, I have to store that at 3050. Fine. Now as I said to you, compare B. This instruction, what it does is, if A is greater than B, or then carry will be equal to 0. If A is less than B, then carry will be equal to 1. Fine. Leaving aside A equal to B right now. If A is greater than B, carry will be equal to 0. If A is less than B, carry is equal to 1. Now this instruction means if after comparing, I am writing JNC address. So jump to address, that address I am not specifying right now, if carry is equal to 0. If carry is equal to 0, that means A is greater than B. That means A is already carrying the maximum number. If carry is not equal to 0, that means carry is equal to 1, then it will simply move to this next instruction. And carry equal to 1 means that A is actually less than B. That means B is actually carrying the larger number. So what I am doing is, now whatever was the larger number, I am transferring that to A. Fine. Write the opcode of this. So this simply transfers contents of B to A. If A is greater than B, carry will be 0. If A is less than B, carry will be equal to 1. And if carry is equal to 1, then I have to make sure that number from B needs to be stored back into A. And at 2000 and C, what I will write is now here STA 3050. So what does this instruction do? STA stores the contents of the accumulator where? At this memory location, that is 3050. So here you will write the opcode of STA instruction from the chart. Here you will write the least significant bit of the address, that's 50. Here you will write the most significant bit of the address, that is 30. Fine. So it simply stores the contents of accumulator at the memory location 3050. Fine. So this is your ST instruction. Now what was the case here? J and C. If J and C, that means if jump, I was actually performing this instruction. In this case, A was already greater than B. I had to actually skip what was written at this step. Fine. If J was already greater than B, I need not transfer B to A. A is already carrying that number. So this instruction would have jumped straight away to this address. So I have to write this address location here, 200C. Fine. So there you will have 0C and here you will have 20, the least significant bit and the most significant bit of the address. So I'm actually skipping move A comma B if carry is already reset. If carry is not set, then I have to actually move the contents of B to A first, so that A carries the larger number. Then I can store that number at 3050. So what we have done, in short, we have compared the contents of 3000 and 3001, and we want to see which one of them is larger. Whatever is the larger number, we have to store that at 3050. And finally, halt this instruction. And halt, you should remember that halt, the opcode of halt is 76. Fine. So this is your program to find the maximum of two numbers and store that result at which location? 3050. So moving on to next question. So the next question now is write a program to multiply. We have not done multiplication. Multiply two numbers, and these two numbers can be any numbers stored in any memory location, or you can have directly some numbers being given to you. Let us assume that we have been directly given two numbers, 03 and 05. So these are both hexadecimal numbers, and whatever is the result, let us store that in the accumulator. So you have two numbers, 03 and 05. You want to multiply these two numbers. So how we are going to do this? So let me explain what we have here. We have two numbers, 03 and 05. So there is no instruction to directly multiply 03 and 05 in 8085. You do not have any such instruction, but you have addition instructions. So what we'll be doing is, we know what is 03 into 05. This actually means we are adding 05 3 times, or you can say we are adding 03 5 times. So you can, using addition instruction, we can perform the multiplication operation. So either multiply 05 3 times, or you can say multiply 03 5 times. So this is the logic that we will be using for this multiplication. So first of all, let us have the two data, and let the two data, let us move the lower byte, that is 03, to register B. So what you have to write, the opcode of MVIB here. You have to write 03, the data byte here. So what does this instruction do? Whatever, you are simply transferring this data byte 03 to register B. Fine. Then you have another instruction. You have to write another instruction, MVI C 05. So MVIC, the opcode of MVIC here. Check that from the chart that we have. You can download that chart, or we have already. I've already provided that chart to you earlier. So So MVIC, the opcode of that MVIC instruction here, and 05, that is the data byte here. Fine. So MVI instruction is basically 2-byte instruction because they are taking up 2 bytes of space in the memory. So it will transfer your second byte to register C. We have not transferred anything to accumulator. After this, what I'm going to do is I need to make sure first of all that before addition, before I actually start adding these two things, so when we add, we have to add how many times. We can add actually 05 3 times, or we can add 03 5 times. So it's better, it is more feasible to add 05 3 times rather than adding 03 5 times, because if you are adding 03 5 times, you have to actually run the loop 5 times. That means each loop will have its own execution time, irrespective of whether the data byte is 05 or 03. The execution time for the instruction will be same. Now if the number of loops will be less, obviously with 05, if we are adding 05 3 times, the loops will be only 3, so the execution time will be less. With 03 being added 5 times, the execution time will be more. So what we'll be doing is we'll be adding 05 3 times. We'll be adding this content to the accumulator. Now before doing that, we need to make sure that accumulator is carrying 00. Fine. Accumulator is basically carrying the data 00, because if accumulator previously was stored with any such because of some previous operation, the accumulator was already carrying some data byte, it's not wiped yet. Accumulator may have some data that will actually cause wrong results for us. We do not want that to happen, because we are not actually touched so far the accumulator in this instruction. We want to make sure that 00 is stored in the accumulator. So I could have done this MVIA 00, but I will not be doing this. Why? Because using MVI instruction will take up 2 bytes of space. Fine. You can see here, if you use MVI A00, it will take up 2 bytes of space. That's not something we want, because you have to write MVI A, the opcode of MVI A here first, and then you will have to write 00 here, so that will take up 2 bytes of space. So this is not a feasible method. If we have already an instruction that will take up only 1 byte of space, and what can that instruction be? That you can have again, you can simply say sub A, SUB-A. Fine. So what does this instruction do? It will subtract the contents of accumulator from the accumulator. So if you are subtracting the contents of accumulator from the accumulator, the resultant will be that the accumulator will now be carrying 00 in the memory location. Fine. So you can use this instruction sub A, or you can use even this instruction XR A. Fine. XORing A with A. So if you XOR A with A, whether it will carry 00, whether it will be carrying 11, whatever be the result, the resultant will be 0, because XOR operation only provides the result when you have 0 and 1 or 1 and 0. Fine. With 0, 0 and 1, 1, the resultant will always be 0, 0. Fine. So you can use either sub A, or you can use XRA. Fine. So you have to write the opcode of XRA here. So the resultant is, in short, it is used to store 00 in A. So we are actually using this instruction to store 00 in A. In actuality, XOR, this XRA instruction is used for XORing, is for doing the XOR operation. Fine. So we have now stored 0 0 in A. Now we'll start the loop, and the first instruction is A D D C. Fine. C is already carrying the data byte 05. We can actually skip one more step. We could have skipped this MVIC 05 here. Let us keep it for now. Let us do this program like this first, and the second time around I will actually show you how we can skip C. We can actually skip C as well. So add C. So once you add C, what does this do? It will add the contents of A with the contents of register C. C is carrying 05, so you have to write the opcode of add C here. It's a 1 byte instruction. It will add accumulator with C, and whatever will be the result, that will now be stored in the accumulator. So we have added 0 0 with 05. So this is once. Now to run the loop, you have to do these operations. Decrement B. B is carrying 03. So once you do this instruction, write the opcode of this. So what does this do? It will help us keep count of it will help us keep track of the loop. So we are now using this instruction. We realize that first B was only carrying 3. Now with decrement B, since it will decrement 1 by 1, so we have decreased B by 1. So now B will be carrying 2. Fine. So that means actually we are reducing the count, how many times the loop has to be checked. Fine. And since we are decrementing B, so decrement B, so that we can keep a track, we can keep a count of how many times the loop has to be run. After doing this, use the instruction JNZ and GNZ to an address location. Which address location? 2005. Fine. So write the opcode of GNZ here, write the least significant bit of the address here, the most significant bit of the address here. So you have 0520. So what will it do? It will jump to 2005 if 0 flag is reset. Fine. If not 0 means if 0 flag is not set, or in other words, if 0 flag is set, is reset, if 0 flag becomes 0. Now when will 0 flag become 0? Once you are actually performing, before this operation you are actually performing the operation decrement B. So B minus 1. So first you have 03, you are subtracting 1 from it, so it becomes 02. The resultant is 02. That means the 0 flag is not going to be 0 flag will show the result. 0 flag is not going to show that there is 0 in B. Again decremented once 0. So on second decrement, B will now carry 2 minus 1, that is 1. Again 0 flag will be will still remain reset because 0 has not been set yet. Once you perform the third time, B is equal to B minus 1, that is this time 1 minus 1, that is B will be equal to 0. So once B becomes equal to 0, 0 flag will be set. Fine. So this is the deal here. Once B becomes equal to 0, Z becomes equal to 1. That actually implies to us that there is a 0 is the resultant operation. So once that happens, you need to end the instruction. You can actually end the instruction, or you can store this result somewhere before ending the instruction. We do not need to store it. Let's end the instruction here. HLT. So for that you can use the instruction 76. So it will automatically end. The accumulator will be carrying the result 15 rather, not 15. This is These are hexadecimal numbers, so 03 into 05. What will be the resultant hexadecimal number that will be stored in the accumulator. Fine. So this is what actually you are doing. You stored 03 in B. You stored then 05 in C. Then we subtracted contents of accumulator from the accumulator. So you can actually draw the flow chart also. Let me draw this properly. Start. The first thing we did is we transferred the data byte 03 to B. Then we transferred 05 to C. Then we subtracted A from A so that the resultant in A is 0. So once you do this, then we added A to C. Then we decremented B. Then we check the condition. So if 0 is equal to, if Z is equal to 0, if this is true, the instruction ends. If this is false, it goes back to this particular location, that is where A will be added to C. So this loop will take place. In the first time, this will be reduced to 02. Second time, this will be reduced to 01. Third time, it will be reduced to 0. So at the third time, Z will be equal to 0. So this becomes true, and it will end the instruction. So what else is happening here? The first time accumulator is added to accumulator was carrying 0, it was added to 5, so 5 will be the output. Second time now the accumulator is carrying 5. This is just for illustration. 5 plus 5, so it will be actually A, not 10. Fine. So the third time, now we are A plus 5, so A plus 5, B, C, D, E, F. So F will be stored in the accumulator. So your resultant will actually be F once you multiply 03 into 05, the hexadecimal numbers. So this is what we are doing. Now I actually had told you that we can make this even simpler. It may or may not, it will require, that operation will actually require lesser space, but it will require more execution time. Fine. So what I'm saying here is, I'm going to show you what I'm saying. Copy and paste. Fine. So this is your original program wherein we had multiplied 03 to 05. So it requires this much of space. 1 byte, 2 byte, 3 byte, 4 byte, 5, 6, 7, 8, 9, 10, 11 bytes of space in the memory location from MVIB to HLT. Now second time, what else we can do is we can actually ignore this instruction MVIC05. Instead of that, so XRA shifts here, XRA A you will write here. So XRA, so you can delete all this. XRA, so B, we are storing 03 in B. X, we are storing 0 in accumulator. Now what we'll do, we will write the instruction ADI05. So instead of, we had actually stored C, we had stored 05 in C. So now with ADI05 we are directly adding 05 to accumulator. So what happens with this instruction is that this instruction has its own opcode, and it has to also, you have to also write the data byte 05 here. So that space will be taken up here. Rest of the instructions will be same. So their DCRB will shift here, JNZ will shift here. JNZ is a 3-byte instruction, and halt will shift here. So initially it was taking up to 200A. Now this instruction takes up to 2009. Fine. So this is taking lesser space, but it will take more execution time. Why it will take more execution time? Because while when you jump back to this loop here, ADI05, we had the instruction in this case earlier. The instruction was add C. Add C is only one machine cycle, that's opcode fetch machine cycle, so only 4 T states. So accordingly you can decide you have the execution time for this. But here you have ADI05. This is 2 machine cycles, the opcode fetch machine cycle and the memory read machine cycle, because you have to read the data byte 05. So it has 7 T states, so it has more so the T states are more, that means the execution time is more. So even though this is occupying lesser space, but because the loop is running thrice, so the execution time has increased. So once you are actually so if you calculate the total number of T states from here to here, keeping in mind the loop, and if you calculate the total number of T states in the earlier program, the T states are less, memory's requirement is more. In the second program that we have written, memory space required is less, but T states will be more. Fine. So you have to actually decide which program you will be using, whether your memory is priority to you, saving memory is a priority to you, or saving space is a priority. Saving memory or saving time is a priority. So you have to decide that. So you can use either of the 2 programming methods. Both operations will give you the same result, but one will take more time, less space, and another one will take up less time but more space. So one, more time, less space. Second one, less time, more space. Okay, so moving on. So let's do a program now. So let's write a program to count number of ones in B register. So you have a data byte in B register. Say for example, it is a hexadecimal number. Can be any hexadecimal number. Say for example 3, 2e, whatever. So if it's a binary number, if we talk about it being a binary equivalent, so it can be something like 11000011, something like that. So you have to check the number of ones in this data byte. So write a program to count the number of ones in the contents of B register and store result in say for example C. Fine. So this is your question. So how you proceed with this? So first of all, let us make sure that we transfer this number from B register to A. So whatever was in this register, write the hex code of move A comma B, and we are transferring that data from B register to accumulator. And following this, we'll make sure we have to store the result in we have to store the result in C. So we'll make sure that C is the result is stored in C. So we have to make sure that C is initialized with 0 0. So we cannot write XRAC here, because XRAC will mean that we are XORing A with C, so it will not make C equal to 0, or we cannot do sub C because it will not subtract C from C. So there is no other option. To make sure that C is blank, we have to use MVIC 00. So MVIC, the opcode of that here, and the data byte 00 will go here. So what this instruction does is it simply transfers 00 to your accumulator. And we'll use one more register, and we are transferring 08 to this register. Why 08? Because the data byte is 8 bits. We know that the data bus carries 8 bits of data in 8085. So to run the counter 8 times, to run the loop 8 times, we need to have this figure available to us. So it's simply, so write the MVID instruction here, the data byte 08 goes here. So we are actually initializing a register D so that we can use it for running the loop 8 times. Fine. So what we'll be doing here is, since we have transferred the data to accumulator, so this is your accumulator. Fine, you have 8 bytes of data. Let it be anything like this: 1 0 0 0 1 1 0 1 0. This is your data, say for example. So what we'll be doing is we'll be rotating this data using the RAR instruction that we have studied already. So we'll be rotating this through right, or we can also rotate it through left, and that's up to you. So with the rotate instruction, RAR, not RRC, we'll be using RAR. RAR rotates the accumulator through the carry. So this data byte will first go to the carry flag, 0 will go to carry flag, and whatever is in the carry flag, that will go to this location. So each data byte will be rotated, will be moved 1 byte to 1 bit towards the right. So this will take place 8 times. So we'll do this 8 times. We'll run this loop 8 times, and each time check the status of the carry flag. So the status of the carry flag will say us whether if it is reset or set. We'll accordingly see how many ones are in this B register. Fine. So we can use the parity instruction to check the carry flags, but we are actually trying to see a different method to find out the number of ones in this register. So following this, write RAR, so it rotates the accumulator through the carry, rotates accumulator through carry. Write the opcode of RAR here from the chart. Now jump if carry is not set. Fine. If carry is not set, if carry is equal to 0, we do not need to do the next instruction. And what will that instruction be? That instruction will be increment C INR C. So it will increment C. So C was actually carrying 0 0 first. So if jump if carry is not set, then this instruction will be invalidated. If carry is set, then if carry is not set, that is carry is equal to 0, then we'll increment the value of C. If carry if it is not set, if it is 0 0, let me write this instruction first here. What we'll be doing after here, DCR D, decrementing the value of the D register. So we have to do this 8 times, so we need to make sure that we are performing this task 8 times. So J and C, this memory location, that is 200A. So if carry flag will be equal to 0, it will directly jump to this location where the D flag will be decremented. You have to write its opcode, you have to write the opcode of INR as well. If carry is set, then in that case INR has to be incremented by 1. So decrement D. After this, you have to again check the status of 0 flag, J and Z, and from here go back to this location 2005. So write the opcode of J and Z, write the MSB of 05, write the this. So you have to write here 0A, the LSB, and the MSB. And finally halt. Fine. C is being incremented by 1. And D is being decremented by 1. So once D decrement is 8 times, after that 0 will be set and it will move to halt. If D each time D is decremented, 0 will be not set, so it will move back to RAR. Keep it rotating. So this rotation will take place 8 times. Every time the carry flag will be checked whether it is 0 or not. If it is 0, then we will skip this part, we'll directly jump to decrement part. If carry is set, we'll increment, every time carry is set, we'll increment C by 1. So at the end of this instruction, the result has been stored in C. That means how many ones are in this B register. So if I show you the flow chart of this, what we are doing here is we actually add that we started with the contents of this. We actually had the contents in B and we transferred that to A. So our data was in B, we are transferring that to the accumulator. Next we are initializing the register C by placing 0 0 in it, and we are initializing counter by placing 0 8 in D register. So these are all hexadecimal numbers. Fine. So these 3 instructions can be written in any order. It's not necessary you write B, you can transfer first B to A, you can write them in any order. Fine. So once this is done, then we rotated R. We use the instruction RAR, so it rotates your accumulator by towards the right through the carry. You can rotate it towards the left through carry. It's one and the same thing. So RAR, and once we did RAR, after that, following this, the carry flag will either be, we check the status of carry flag, if it is equal to 0 or if it is equal to 1. Fine. If it is equal to 0, next instruction that I am going to actually write here, if it is equal to 1, it will increment C by 1, so that if carry is equal to 1, that means there is 1 in the, which actually we are trying to see how many 1s are in B. So if it is equal to 1, we'll increment C by 1, so that we get the impression that C, there is one at least in C, or after running 8 times it will see how many 1s are there in this B register, or that's actually now stored in the accumulator. If it is equal to 0, then it will directly jump to here, which is decrementing. So in either case you have to decrement D register. Fine. So after decrementing D, you check the status of 0 flag, if 0 is equal to 0 or not. If 0 is equal to 0, if this is true, then in that case end the instruction. If it is not true, if it is false, then go back to this particular point, rotate it again, check again the status of carry. So this will take place 8 times, because accumulator has because D is carrying 8, D is equal to 8, so this will become equal to 0 only after 8 times being decremented, after which this 0 flag will become true and the operation will end. So these are some programs that we have done today. We'll continue next session.